Hello, my name is Keegan Churchill. My partner Nicholas Wells and I have spent the last 6 weeks developing a rules-based AI that plays Starcraft Brood War. This project is the final project for CS4303. The main goal of our project is to beat the in-game AI decisively and achieve the highest win rate in the student competition. This project is important because practical, low-cost, and non-deep AI solutions to real-time strategy games and their neighbor, dynamic decision-making in the human world, are still very weak compared to professional humans. Developments in this field could mean more people could have general access to affordable yet high-performing AI systems, rivaling their deep counterparts, which are very expensive to produce. Nicholas and I split the project into two categories, micro and macro. Put more simply, Nick will destroy the enemy, and I will provide what he needs to run his war engine.
Within our bot, we are trying to solve the problem of winning the game. To solve this problem, we developed a systematic approach to solving the problems we were faced with. Our big initial problem was, how do we build an AI bot for Starcraft? And so we decided to split that within the main functionalities of the game, which include base building, scouting, and attacking. From there, we began further developing our strategies and ideas for these concepts. Within building, we had to figure out the problems of how do we build multiple bases, how do we find those locations, how do we know if an enemy is at those locations, and so we developed systems and strategies to discover that. We also needed to know where and how to build a structure, like the resource requirements or technology requirements. This was another problem we solved. Related to scouting, we needed to figure out how we could both find an enemy base and a systematic way to find enemy units no matter where they were on the map. Related to attacking, we needed to have a way to organize our units so that they perform properly, how they should attack an enemy when they are faced with it, and along with that, how we decide when we attack the enemy base. By subdividing these problems, we split the problem up into smaller chunks that we could both, as partners, split up evenly and work on individually, allowing us to work parallel on ideas while still completing our objective.
So I'm going to do an overview on the methods and algorithms I used to solve the problem of defeating the in-game AI with macro. And main things that I did first was I split the workers up immediately for mining, and I assigned them all their own mineral fields. So you'll see that the pros will get evenly distributed among all the minerals here, and they'll double up, and there'll be a maximum for 2 minerals per resource, with the chance of going beyond that if, let's say, a expansion dies and the probes will have to get transferred over to here. And when a new base is rebuilt, all that will get rebalanced. Another algorithm that we implemented was resource allocation. So there'll never be any contingency among probes and bases for resources. Whenever a probe is sent to build something, the resources it's sent to build are tucked away, and no other thing can be built using those resources. However, if the resource amount goes over that amount, they still have access to that, so there would be no holdup. This is my base analysis algorithm. You can see this green circle is actually encircling the base. The center is actually the average position of these resources. And you can see, if you just hop around here, you can see this is a circle of the base, this is a circle of the base, this is a circle of the base, and you can see it's actually smart enough to ignore outlying resources like this one here. It doesn't get wrapped in to these other bases. And it does that. We filter it out. First we check if the minerals are below 500. If they're below 500, we consider that pile not to count. And also, if it is too far away from a subset of resources. So unless it has 4 neighbors or 3 neighbors, making it a set of 4, it will get called out of the pool. And then that's how we find resources. The base analyzer is great because immediately on startup prints out all the bases and the IDs of all the resources for each base. And here you can see this map has 15 bases that we can quickly verify. 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11, 12, 13, 14, 15 bases. So here we can see the resource allocation manager. And this is part of the base manager that manages all the bases, and it controls how much minerals each base can use and see. So here you can see our actual minerals and then our tied up minerals. And you can see when it goes to build something, as it's going to build something, it ties those minerals up, reducing our total minerals in the perspective of the worker commands. And that way we never end up going to build something and have it be canceled due to insufficient funds. So we're going to just do a quick dive into our take on doing a build order. I ended up not going with a queue approach. I thought that it could be too complicated to account for all the scenarios where they destroy pylons and that messes up your supply count, and so you can't do it based off supply. If you just do it by a fixed queue, then if something happens and something's delayed, you can't build things concurrently because they're waiting for the next thing to pop in the queue. And so this was kind of my solution, where essentially that we want to make sure if we're going to build a forge, we want to make sure that we are not already going to build a forge, that the forge isn't building already, that we aren't going over the maximum forge limit, which we want to have one forge per base to a maximum of 3, so 4 bases will still have a total of 3 forges to really pump out those 3 upgrades simultaneously and overwhelm our opponent. And here we have to make sure that the minerals that we have, minus our tied up minerals, are greater than the value of minerals that it costs to build the forge, in this case 150. We also want to make sure that we prefer gateways over forges. So we want to make sure that if we have no gateways, we would rather build a gateway than a forge. So just make sure that the size of the forges are always less or equal to the sizes of the gateways. We also want to save those 150 minerals for a cybernetics core if we can. And all this trickles down to kind of produce a build order, but it's so agile that if something goes wrong, there's all the things that it will do with the money in an instant. It doesn't have to do any thinking. It just does it. And here we can see we're running our bases for every base that we have. We make sure that it has a nexus before we decide to train any workers at it. We're training dragoons, and then we want the dragoon upgrade, and then we want to train zealots near the bottom. So we're preferring dragoons to zealots. So if there's a space open and we can afford a dragoon, we'll build it. If not, though, we'll immediately build a zealot just to keep that production going. And we have the upgrades being built. All the forge upgrades will be researched if we had the required tech. As of right now, we do not. So now we'll just take a moment to look at how it builds exactly. And you can see that it prefers to put the gateways out on outer rings, while forges and tech facilities will tend to be in this pocket here. However, I added an element of randomness to just get out of any ruts that the computer may get into with returning positions that it cannot build with. So you can see that here the tech buildings are always end up kind of in this downward direction, while the gateways will always be in this outward direction. Usually the cannons will be between the gateways and the tech facilities. You can kind of see that here, where the ring of cannons is kind of behind these 2 gateways. However, you can see the randomness has put the tech facilities a bit further than where they normally go. Here you can see that they're getting the dragoon range to go and march out and attack soon. And here you can see the tech facility getting again tucked back by the mineral line. And we can quickly just see again and just see how it shows this time with the randomness and the bias that it has. And the spacing is achieved, the early on spacing is achieved, although things start to tighten up as the building area gets smaller and smaller. The initial spacing is caused by giving all the build position arguments the argument of a nexus, and then taking that position and then getting it the argument for itself. So basically it gets a position where a nexus can fit, and then from there it takes the most desired position where the actual size of the object can fit. And it just helps maintain spacing. However, right now expanding is turned off. Normally if you be expanded, that'll increase the spacing a lot more. And again, you can see the tech facilities are in this inner ring. The cannons are in between them and the gateways. This makes a pretty nice defense because it gets really hard for enemies to reach these cannons as they become more and more embedded into the wall. And pylons are actually the ones that don't really have any bias. I kind of try to scatter them as much as I can in order to increase the amount of building opportunities. But again, they still follow that nexus spacing until the mid game. I use a heuristic for the mid game. When I reach about 50 or 30 some odd supply, then I say, okay, we can start sticking the pylons in wherever you want. It just stops us from sticking the pylons in, let's say, the way of a gateway or in the way of a simulator or the mineral fields. But later in the game, there's so many probes that it can't really build it there because there's too much obstructions.
The methodology chosen to complete the combat requirements of our bot was a army-like structure. We begin on the lowest level with our custom base units. These units are designed for our bot to have knowledge of how a unit works outside of the game. This is used to enable per unit commanding, allowing every individual unit within our bot to be given orders, but also be able to do unit-specific commands that relate to only them. This includes the use of the selecting the closest unit to attack algorithm. The closest attack algorithm allows a unit to pick the closest target that's to it based on that unit's ability to fight the enemy. If that unit cannot fight flying, it will not target flying. If it cannot attack ground units, it will not attack ground units. It'll pick the closest unit to its fighting type. This advanced technique also enables our unit to select enemy units over enemy buildings, which when attacking an enemy base, the units controlled by our bot will focus on the enemy's attacking units instead of the passive buildings and workers. By having these custom base units, we allow for per unit control, which enables the discussed behaviors. The next level up of this structure is our squad class. These squads contain the ability to have a smaller section of units ordered to do specific tasks. At this point, our bot does not avail of that tactic in any extreme way, excluding the simple keep formation command, which keeps our squad units together as close as they can be. This prevents units from straggling across the map in a single file column, and when attacking with an army, they will stay clumped together. This also enables a further benefit to when a squad is attacked, all units within the squad are very close to each other and should, by a result, attack the same enemy or the same small group of enemies, which should create a higher damage output, which should allow the squad to survive fights in a more efficient manner. Within the squad structure, we save units using a map system. It maps the unit's in-game ID to the custom unit base system. This was chosen as units die and are created on a very frequent rate, that this system is the fastest way to access units by their ID, but also be able to remove them by their ID in a fast and efficient manner. After our squads, we organize them inside of our army. The army is a single class used by the bot to manipulate our squads, which manipulate individual units to do the orders that we give them. Within the army, we also use a map to tell not to the unit ID to its custom unit class, but from the unit to the squad it belongs to. This is used as a sure way to make sure when a unit dies, we can find it within our army structure and remove it properly. Our squads are in a vector list as we do not remove squads, and our filling mechanism adds to the first squad that can fit a unit. Our army accepts 3 types of orders: a default order, which operates when there's nothing else to be done. When the bot decides to attack, the attack order is then given, which will then gather up the units to attack in the specified manner. And we also have the last command, which is our scout command. Our bot gives the scouting order to the army, which is then given to the scout squad to move to that location and scout that location as seen fit. Within the army, and with all 3 subtypes, at this current state in the bot, they do not avail of the intended behavior of being unit-specific or squad-specific. Given more time, which we ran out of, we could design squads to be specific to a set of units or a type of unit. We can develop further classes based off the base squad that behave in unique ways based on unit types. We do not currently have this as we did not have the time to implement it, but the framework is there to enable complicated behavior based on unit type in the future. Scouting is another area to which specific algorithms and methodologies needed to be applied. To avail of scouting, within the army structure, we created a scout squad. This squad was used to scout the map based on the orders given by the bot. The bot gives these orders based on a two-system structure based on first, it goes to every starting location and scouts that location. The second part, it uses a structure of the last not seen location on the map and moves to it. Within that structure of moving to those locations, we store information based on the order's location. This structure is then further used when we attack, as we choose the locations where, given an order's location, we tally up the number of units seen while performing that order. We use that later on within the attacking to decide what locations to attack. A further enhancement would be to have multiple scouts, enabling us to scout more than one location at once, allowing us to perform a quicker scouting operation and providing better, more accurate information. We attack by first scouting the location and getting that data described in the scouting section. Once we have that data based on the positions, we use a hard-coded set of checks to make sure that we stand a chance in winning an attack against the enemy, and if those checks pass, we attack the enemy by moving to the order location with the most enemies seen. Although our AI was required to complete 1,000 games against the in-game AI, we did not properly plan enough time to complete a whole 1,000 games. And so we went to the number of games that we could complete within enough time to finish the video and complete the other requirements of our project. As a result, we only played 204 games against the enemy AI. The results show that our bot wins from our 204 games played a percentage of 36.3% of the time. This overall doesn't meet our goals, but it does have a good representation of a good starting point, which with further time our bot could further improve. Against the Terran we had 32.8%, against Zerg we had 34.1%, and against Protoss we had 43.6%. So our best enemy to fight is Protoss. In conclusion, our bot did not meet our initial goals. We do not beat the AI most of the time, and as a result, we do not beat the enemy AI most of the time. Our statistics also shows that we did not run the entire 1,000 games. This means that our statistics are not as accurate as they should be. After completing the project to this point, we both realized as a group that there's areas in which we placed time and effort that did not pay off in the end. One such area is the scouting mechanism, as it currently is very rudimentary and does not provide accurate fighting data. In playing games, we notice that our AI tends to have a problem finding the enemy base later in the game, and as a result, our games can run much longer than they need to. Another issue is the formations of our units. When building the base, our units end up getting stuck and jammed within our own base structure, and as a result, when ordering to attack, we sometimes don't get the entirety of our units to attack the enemy, only a certain portion of them.